Thank you very much for the introduction. My name is David Reis, as Sebastian mentioned, and I'm here to present my paper on regional differences in configurations of energy communities, future scenarios, and policy implications. So, as we've heard several times throughout the last few days, and as we're all aware of, we're faced with an increased number of distributed energy resources in distribution systems. So this is on the one hand distributed generation, mostly PV in residential systems, and on the other hand, distributed flexible loads. So for instance, electric vehicle charging or heat pump systems or battery energy storage systems in a residential context. And these developments open up some potential for new roles for end customers. So they could engage in energy trading or energy sharing with their neighbors within the distribution system, for instance. So why does this then motivate energy communities? Energy communities have actually been introduced into European regulation in the Green Energy for All Europeans package in a few years ago. And to highlight the view of the European Commission as on energy communities as part of their strategy to tackle the energy transition, I've highlighted or I've put up one sentence that they published on their homepage to promote energy communities. So energy communities enable collective and citizen-driven energy actions to support the clean energy transition. To rephrase that, energy communities are associations of end customers. They, on the one hand, can engage in generation, consumption, sharing, and trading, but they can also make joint investment decisions in energy infrastructure and help the energy transition. So it's really about engaging end customers and making them part of the transition to support increased renewables in the grids as well as other infrastructure. So it's quite interesting that energy communities have quite a few differences in the way they are realized in different countries. So I want to highlight this on the example of the DACH region, so Germany, Austria, and Switzerland. For instance, in Switzerland, energy communities can be realized in various forms, but they have the restriction of having to be behind a shared meter. So you cannot use any public grid infrastructure to do sharing or trading of energy or operate sort of joint energy infrastructure. In Germany, this is also quite restrictive. So there, the energy community concepts are limited to more or less joint generation units without any sharing or trading between individual end customers. And in Austria, we actually have some regulation on how to implement local sharing or trading with static prices and a static community market that can have dynamic or static allocation of power that is generated within the community. And I'm focusing this work, or the communities that are presented in this work are focused on the Austrian regulation, renewable energy communities, and also only on the local type. So this is in a common low voltage grid. There's also regional type that has also customers within the same medium voltage grid. So the overarching question we want to address is how energy communities in future might influence the rest of the energy system. And the first step in my mind is to get a clear view of what an energy community might be in the future and what types of energy communities might form. So the methodology we followed to reach such community models was as follows. So we started out with several assumptions. So number of members, number of heat pumps, EVs, and amount of PV within a community. From that, we reached a hierarchical scenario with different technologies clustered within end customer energy systems. And we ran these community scenarios through yearly simulations to gather residual power profiles for each of the customers and an aggregated power profile for the community as a whole. These aggregated power profiles or residual power profiles are then put into a mixed integer linear programming model to optimize for optimal community storage or generation size, or optimal investment in community storage or generation size. And in the end, what we get out of that is then a realistic model for an energy community that might form with given the assumptions we made at the beginning. So I want to go a bit more into depth of how we handled the simulation of the individual customers and the community as a whole. So the first point I want to make is that it's quite important to separate devices that are within a household and devices that are sort of shared with all community members. So a household might have PV on the roof, might have a battery, might have a heat pump, might have electric vehicle charging, and the community might have shared PV and might have a community battery. On the one hand side, the community members are responsible for the operation of their own flexible load technologies and everything that's contained in their household energy system. And there needs to be some sort of central entity responsible for management of these shared assets. And also for settlement of local energy markets. One important point I want to make is that next to the regulation enabling energy communities, it's also important to look at what type of energy management capabilities are present and what type of ICT infrastructure is actually in place that enables communication between the different actors in the energy community. We addressed this different availabilities of technology in 3 control scenarios, and I quickly want to go over these. So the first one is the reference control scenario. This is sort of the minimum that needs to be in place for a joint operation of a storage capacity to even make sense. So in this case, within the community member household, there's some sort of measurement entity that receives data from all the flexible load components or all the distributed energy resources within the household energy system and passes that on to the community management entity. On the community management side, we receive the information from all the community members, and we use this information to control the storage for the current simulated time step and to also simulate or settle the local energy market. Going one step further, when we assume that there's also a home energy management system present for every community member, there's the possibility to optimize or to activate flexibilities in-house. So you can react to your own PV generation by activation of electric vehicle, for instance, electric vehicle charging, or by preheating your house, for instance, with your heat pump. In this scenario, though, we still don't have a bidirectional communication option from the community members to the community management. So there's no information on whether neighbors are currently producing any energy or whether there's any excess generation available. That is addressed by the central control algorithm that we implemented. So it's the same as the local control. So each community member first tries to use the in-house generated energy and then provides information on what is actually excess currently generated for the current time step. Provides that information to the community management, which then passes this information on to all the other members. So the paper had in its title, Regional Differences in Energy Communities. How did we address this? So we constructed several scenarios we looked into statistical data that was available on different technology distributions or penetrations, and settled on using 3 distinct NUTS-3 regions of Austria and mapped the data to these regions. The regions represented each a type of region. So we looked into urban, suburban, and rural environments, and there's some details on the regions on the slide and even more in the paper. And in the end, we ended up mapping this statistical data and the projections for future, so for the 2030 scenario, which are also not explicitly listed here, but in the references of the slides, and also can be found in the paper. We mapped that onto real grid data from these types of regions. So they were not exactly from these NUTS-3 areas we selected to represent the area types, but from similar types of regions within Austria. In the end, we ended up with over 15,000 communities or community scenarios, more or less. And the first result I want to share with you is that community storage really takes some price difference between energy provider price that you need to pay and feed-in price to be profitable at all. So with our assumptions, we only saw the mixed integer linear programming model settle on installing community storage when the price difference was higher than 20 cents. So yeah, high prices at low feed-in reimbursement increases the storage profitability. The second result I want to share, so on this graphic, we see on the x-axis the community battery energy storage capacity in kilowatt hour per community member. So to normalize it between the different regions, because urban grids that we used had over 100 participants, and the rural, I think the smallest one had only 20 members. We wanted to analyze how these different availability of energy management capabilities and communication capabilities between the actors in the energy community affect optimal storage size, so optimal shared storage size. This graphic is for the 2030 scenario, so it's a future scenario, and the mixed integer linear programming model was also able to install additional PV generation capacity to the storage. What we see is that where there's a lot of generation available, so especially in the rural and some of the suburban cases, the mean community battery capacity per member is significantly lower when you're considering a sort of local demand response measure that could be said to be the central control algorithm or the central control paradigm. Yeah. This I'm going to skip over and sit for the sake of time. These results, we actually also wanted to have a look at what's the residual costs, the total energy costs for the whole year for each of the community members. And what we see here, so each of the dots represents one simulation and consecutive optimization, and then the result of the community battery energy storage capacity per community member for the different region types. And the main takeaway from this figure is that really community energy storage only makes sense, or the optimization model only settled on installing it when the prices were quite high. So when the energy price was high, when it's low or even negative, there's almost no installation of storage. We then mapped the residual power profiles onto CO2 intensity data from electricity maps. I think we heard about this as well a couple of times in the last days, to quantify what this means for the emissions of the energy use of the end customers. And we also included in this calculation the emissions created during the production of storage systems and also generation capacities. What we see on this graphic is a trend towards lower overall CO2 emission per energy usage, per yearly energy usage, when there's more storage capacity installed. This makes sense intuitively, as you're able to use a higher portion of the local renewable energy generation when storage is installed. So to conclude this talk, we've seen this approach is suited to determine economically optimal future scenarios of energy communities, given the assumptions we made. And depending on future energy prices, communities might emerge, operating shared storage and generation capacities. So we might see a future where really end customer driven energy infrastructure is present in our grid. And we also saw that the combination with demand response schemes local to the community might make sense, as it's potentially offers the possibility to reduce the capacity that is actually needed or that is economically optimal. And we saw a large difference when looking at area type. Particularly, this is the reason because there's a varying, so that the factor of generation to load overall over the whole year is quite varying between different region types, and technology distributions are also varying throughout these regions. So what is future work, or where do we go from here with this created initial community models that were a result of this work? So on the first hand, I want to introduce another control paradigm. So I would like to look into reinforcement learning to optimize each of the community participants, rather than using these rule-based control scenarios that we use now, maybe looking into more optimization-based control for these. And the second big part is to analyze the effects of these communities and their implications on power grids. So how do the power grids react when such a community is actually implemented in the end? And also another point is that we want to look into ancillary services. So what is the implication when we're looking into these community batteries actually providing a service to grid stability for the distribution system? And with that, I'll end my talk. Thank you for your attention, and I'll take questions.